Okay, so let's start the afternoon session. So our first speaker is Sabyasachi Bhattacharya from CREST in Calcutta. Sabyasachi is going to talk about 2D, quasi-2D crystallization or granular self-organization.
Thank you. Can you hear me? Okay, I'm an imposter here and a gatecrasher in some sense. But Deepak's honor was far too much to resist, so I'm here, and I won't say very much about that because I have an evening duty, and there I'll have something more to say about our association together for a very long time. Now, I have a few apologies. This is an experimental talk, and this is probably the only experimental talk. And so please forgive me. I mean, there is something called experiment, and this is not going to be a simulation. This is not even work in progress. This is work in the beginning, and it's the last talk I felt rather bad because we're going from the sublime to the ridiculous almost. So it's basically an undergraduate talk. And the title, Roll and Stumble, is actually a play on chemotaxis called Run-and-Tumble. And you will see if this play has any merit beyond the linguistic connections. What I have done, because of the last 2 days, I have seen so many equations that I have taken all equations out of my presentation. There will be no equation, only pictures and videos. And you can ask Q&As. But if you fall asleep, I'll greatly appreciate if you just wake up randomly and say, wow. So that would be much appreciated. However, I want to say that this is not entirely a frivolous exercise. This work is related to friction. And it is based upon a set of work that my colleague Shankar Ghosh at TIFR began. And the work I'm going to tell you is also their work, that group's work. And there are two precursors, this one and this one, which has all the formulae, in fact, some math that even I don't understand. And it has everything, all the equations, all numbers, all everything. So now just relax, watch what I have to show you, ask a question if you must, but applauses will be very welcome. Let's see what I get here. What I'd like to, I won't tell you anything about what it is, okay? These are, just first watch it, then we'll see. Okay, so these are objects which are rattling around in what looks like a dish, and they are just rattling around, and just what it does. Thank you. Okay. If the first time wasn't sufficient, I'm hungry for compliments. Another round will be good. All right. Okay, enough. So, oh, okay, I'll come. All questions will be answered to my ability. Okay. So what I showed you is something that happened forward in time. If you go to the internet, you will find tons and tons of stuff called reversed in time. And this is my favorite one. I just love this one. I won't show you everything, but I'll show you a little bit. It's a young man who likes to show things time reversed in a movie. So just watch them. This is a crushed beer can. You know, I asked many people, you know, is this possible? They said, apparently some Tibetan monks know how to do this. But normal human beings don't. And this is yet another one. I'll stop at the fish one. I love this one. The fish jumps up, that's it. Okay, enough. All right. Okay, so what is it that I just showed you? What I showed you is a petri dish kind of thing. Petri dish is, those of you who have forgotten chemistry, it's a flat dish, and there are donut-shaped particles on it. And these particles are donut-shaped. So if you look sideways, they look like this, but they're quite spherical. They're basically these plastic beads that you can make, you know, a ring, I mean, a sort of a ornament out of. And it has a hole through it. And the entire purpose is for you to understand that this is lying face down and the other is lying face up. So here, by the way, these the connection to the Argentinian color was accidental. All right. Okay, I'm sorry. Sorry for that joke, all the French folks. Okay, so the idea is that you just let this, this is not even a good one. It just goes, runs into something and tumbles, okay? So this is what is going on. So you put them down because clearly this one is not as stable as that one, right? So although at very high impact, it can be made to stand up. But mostly what it will do is if it were like this, it will fall down through collisions. So that's what they are. And they begin by being mostly put in, mostly edgewise. And if you see where they end up just one more time, last time, never have to see it again except at the very end. And this might mean something more. Okay, so you now begin to see that they're turning sideways now, right? With a stable way. Okay. And then when they are a single crystal, they're all sideways. So there is obviously no roller in them. Okay. So you can call them slider. And they are viewed with a camera which is co-moving. That's why you don't see the movement of the plate. You only see what's going on in the system. Okay, so so if you just look at what happens, time evolution of rollers into sliders. So once again, this is a roller, to remind you, and this is the slider. Okay, and I won't give much away. I'll come back to your question a little bit later. The petri dish is in an orbital shaker. You know, the orbital shaker does not spin. It basically goes around. This is used in every biology labs. And you know, in TIFR biology labs are so rich that they give away the old ones. So we just got one of them. And it just rotates in an orbit, okay, without spinning. I don't know how important that is. Just. Yeah, it's all the same. It's all the same. The parameters will change, but they will all do eventually that. I mean, you can shake it like this. No, because we don't want it to jump out, because we are trying to keep it in the plane. You can, the PNAS is the full 3D. So you can look at the full 3D there, right? It's very complicated. I just didn't want that here. So you can look at that. So they basically go from one to the other, and this is roughly the evolution. And that arrow is telling you where the clustering becoming visible. But these are small number of particles, nowhere near Avogadro's number, and so one shouldn't think that that's what it is. But they're going from rollers into sliders over period. There are 260 frames here, and this is roughly how they change. Now, usually at this stage, people say that, why are you looking at a disk? Why aren't you looking at a sphere? Because if rolling and sliding is going to be the issue here, go to spheres. And that's what we did. So we had a single loop of moving this rotation rate of the mover was increased very, very gradually. And let us see what happens next. And this is the same dish. And see what happens. This is time has been, why is it not showing there? Oh, time lag. What is going on? What? This is very strange. Does anybody know what might be going on here? It's too much? Very staccato. Well, let me just tell you what you are seeing here. The rate of rotation is being ramped very slowly, quasi-statically, if you like. This entire thing is half an hour. Okay? And so we're increasing it. And as we increase it, there is a range of rotation where you saw a crystallite form. Okay? And that crystallite formed, and the others didn't join up the crystallite. They just were hanging around. The ones that you see as lines, these are capturing moving particles in the video, right? Is that clear? I'm sorry about this time lag business. I don't quite understand what that is. So what we want to do is want to do it twice. Because if you have done it once, you do it twice and see if you see the same thing. And this is also doing it is kind of slow. But now the crystallite formed, but in a different location. Okay, so it wasn't something magical about that location. It was just some location. And if you do it many, 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 many times, you will find the same thing happening in different location in the system. So it goes into that state. So crystal forms at different location. That basically says that the underlying potential, friction potential, or pinning potential, if you like, is sort of average. It's what in language of pinning, we call it weak pinning regime. And then it melts at sufficiently high moving rate, this crystallite actually falls apart and is only just moving particles. Okay? So what you essentially find after a lot of work, that there is a steady state in some intermediate range where crystallite coexists with the gas of rollers. Okay? And you may wish to ask this question, that can that be converted into a phase diagram of something, like a dynamical phase diagram? And let me explain this one, because this is perhaps only central data that you need to. So F is roughly omega square r. So this is the rate of rotation. And the maximum we use is about 10 G. That sort of gives you the ballpark. 10 G, 10 acceleration due to gravity. And that is roughly on that side, that axis. We call it drive. This is the volume fraction or area fraction, if you like, of the particles. They're very small, very, very small. And there is initially at low drive, everything is stationary until you overcome a threshold for motion. Because there's friction and it's holding it back, and you overcome, and then you have a region where there is some part that's a crystal and some part which is a gas, and the crystal is stuck in the frame of the moving object, and the gas is moving, right? And then above some line, everything goes. Okay, so they're all now scattered all over. Okay. So then again, what you wish to do is you wish to do up and down. Okay. So what you want to do is you take a point on here, and you go up and you come down, and you see what happens. Okay, to the mobility. And what happens is the mobility, nothing happens, then it becomes mobile, in somewhere. Then you come down, has a very pronounced hysteresis, and then it comes back down. So in the language of phase transition, which I'm kind of pushing you towards thinking like, but may not be a good thing to do, it looks like a first order phase transition of a coexistence region of a crystal with gas. And then, this is the phase diagram, and this is kind of the first order phase transition. Okay, so now the other game you can play is when it's moving very rapidly in the coexistence region, otherwise the coexistence region. And you do what we call a rapid quench. Okay, so this old days, those of us who used to work on med classes, you just take it up and just go boom. So we just stop it and then see what happens. So that's what this is. I hope this is a little bit better. All right. So the reason it took a little while, because they were inertial, they were moving around. And now you do not have a crystal, you have a distribution of clusters of various signs, starting from single one all the way to large one, but the large ones invariably have defects in them. So the analogy to things we know in conventional phase transition begins to become a little more enticing, that maybe that's the way to think of this weird phenomenon that we're looking at. Now, what might be causing all this? Okay. So let me now show you a large crystal, which was formed very carefully. And there's a very large crystal, which is in the middle. And you can see it's quite faceted. And now I'm just going to show you what happens. Okay, so everything is moving, by the way. Okay, so the gas is moving, and the crystallite is in the center. It's at rest. And if you just keep watching this movie, as some of us experimentalists love to do, we keep staring at it, you can see that all the action is at the edges. Okay. There are, they're knocking some off. This is a good single crystal with one single dislocation line. I don't know if you can see that dislocation line here. Okay, there is one dislocation. Otherwise, it's a good single crystal. And this is what it does. Now, this is the same one. So what happens? I'm trying to summarize what we find. It's a steady state, action all at the boundary. Flux in is equal to flux out, meaning the particles that are being thrown out are equal to the number of particles which actually get stuck. So this is a clear steady state. Now is the mind-blowing result. At least my mind was blown. And that is Shankar and his students, they came and said that we can't believe what we are seeing. What we did was we cooled this, what they did is they cooled this damn thing down, okay? And then with a spatula, they removed all the particles that were there rolling around. Okay, now they're gone. The rollers are gone and the crystal is there. Stop check. I'm sorry, my nomenclature. Yeah, no, nothing was cooled down. Sorry. It was slowed down and then the rollers were moved away. Everything is a roller. You can see, I'll show you that they are all rollers. These guys are, what they are not doing anything. They are stuck. They are not moving. I'll show you just in a second how this happens. And if you remove all of them and you then ramp the drive back up, what do you think happens? Oh, sorry. Too late in the day. All right. So the crystal becomes a little smaller and some number of rollers now appear. Okay, so it immediately suggests that you are looking at something which has surface tension. Okay. And there is a kind of a quasi-steady state where there is a balance, how many are floating around and how many are in the stuck state, all right? So the particles at the boundary are changing identity, and this is not completely correct, from a roller to a stationary one, because the stationary ones aren't doing anything. So calling them a slider doesn't make sense, except later, as I'll hopefully be able to show this to you.
You always have just one.
Here it is. It shows ripening. Okay, I have stopped at calling it Oswald because that's getting too far. So, and it always has facets. As long as the crystallite is large enough that the faces are many particles wide, you clearly see that there are facets, and it shows ripening.
Saying this, they're tipping, they're
No,
going.
I'll come back. So take a look at this. If you still have a question, I'll come back. Answer. Okay. So the point is that what is really going on? The collisions are going on, right? So let's look at collisions. So I'm going to show you the simple collision. Okay. You want to see it again to convince yourself that these are rollers? They were rolling. Right? Isn't that obvious? They just came by, they rolled, and they moved away. All right. What would happen if I had more? Okay, so this is, we call a binary collision. Now, suppose I don't have two particles come in, but somehow I have 2 and 3s, dyads and triads. What do they do? And let's look at them. Okay. I'll show it one more time. Okay, now focus on this fellow. All right. So, and what does this tell you? It basically says, let me just now. They're attractive interaction. They come together and they stick. If the approach momentum is not sufficiently large to move them away, then they will have a binary collision. But occasionally there will be some which will be together. And the third one, you noticed here, it came, hung around, rattled, and so on, and then formed a triad, and it got stuck. So what happens? What happens is that a dyad can only roll perpendicular to the line joining their centers. Yes. Look, if there is static electricity there, nothing like this is possible. You charge them and they just fly apart. Okay, charge is out of the question. Okay, so this is, no. You get charged stuff and this one will not happen. Charged stuff will do Wigner crystallization, right? Or ought to. There is no similar charge, but dipole and a van der Waals, that must be. So now the thing is that a dyad can only roll perpendicular to the line joining their centers, and a triad cannot roll at all. There's some attraction. They're moving around. They have come together and they are moving. This is what you saw here. I think van der Waals. What else can there be? Yeah. No, I don't, it's very hard to know what makes them stick, except that sticking is not a very highly probable event. Mostly it doesn't stick. But once it sticks, once three stick, then they become immobile. Right? No, but here our best guess is that these are attractive interaction between them, sufficiently large that for small impact, some of them will actually stick together. And the more important question, which I think I have messed up in removing too many slides, is that the coefficient of friction for sliding is about 20 times larger than the coefficient of rolling. Okay, so sliding is not happening. What's happening is immobilization, if you like, unless you move to such a large drive that whatever be the sliding friction, it overcomes that, then it slides. Let me just show you some more. Yeah.
If you stop shaking, the triads stay as triad.
Yeah. And so what are the triads? Triads are the seed around which the crystal forms.
And when you shut down the shaking, the triads remain.
Triad
So
remains.
there is an attack.
Something, yeah. Short range attraction. We figured van der Waals. I mean, what else? So now let me just show you something which is much more. How am I doing with time, Satya? Oh, that much. Okay. So these are steel balls. Who was asking about steel balls? Somebody. Okay. Here is your steel balls. So there are three of them. The single one, the two, and the three. Okay, they're put on as horizontal a plate as we can possibly get on a lab. And we just have put them next to one another. And now let's see what you can do. Take a single one, and it is probably Deepak's hand or Shankar's, and they push it. Okay, so let me just stand here and do this. Okay. Clearly, it is, if you just put a white spot on it, you will see that it's actually rolling and it's not sliding, obvious. Right? Next is two of them. Okay. Now, in this particular case, I think a little bit of small glue was attached. Yeah. Okay. By themselves, they don't stick. They stick only occasionally. But I'm saying that there is impact, right? So two things which come very close together. No, there will be roughness on the surface. I don't think it's better than micron. It's much better than micron. 1/10 of a micron at least, better than your hair, for sure. These are. Look at number 3, because this is the most interesting one, and I think this answers your question. Okay, so it rotated around each other. Okay. When they're rotating around each other, they're not rolling. So that you could say is something like a slider. It is actually rotating around. And no. No, they're not magnetic. With this one, this is by finger. Just the picture. This is how we are rotating. Okay. Let me just show this one more time. This might be a good time to just take a look at this. Okay. So what is happening here is they are basically not hitting each other. Okay. They are not forming, how should I say, this happens. So it happens because a nucleus happens. Then particles come in and hit it. If they hit hard enough, then they will break it. If they hit it slow enough, then they get stuck. So let me just head back and get to, I'm sorry that I'm being vague about some of these issues. These are critical issues. Okay, so you saw this. So what can we say about rollers? Okay, so I'm claiming that rollers are different from sliders. So how do I know? And that is, I had one more. Oh, there it is. Okay, so I can take this out, undo the Argentina, and now you can see that I cannot roll them together in the same sense. If this rolls, then if this is in contact, it has to roll the other way. So they cannot roll together in this sort of, in this kind of format. But if they are like this, and then they want to slide or stay together, there is no problem of them staying together. So this picture of the disk with the hole in it, it shows you that if you have the sliders, you can create a nucleus and then it forms. So therefore, this picture that I showed you before, when it all crystallized, they were all like so. There was none which was like this. So it is only that. And it all depends. So I'm just showing you examples, but let's just keep going. So typically sliding friction is much larger. Typical number will be like 25, 30 times larger. Sliders with low mobility, they form temporary nuclei of growth. And rollers with high mobility, they arrive and join in time. And this is very important. That is, if everything starts out this way, and we had a conversation about this before, and I think you were right, it's just time is much larger. The question Sriram asked me before is that if you put them all like this, will they crystallize? And the answer is yes, but it takes a very long time. And it takes you to a different parameter space where you need to make them move. So rolling allows the particle to arrive in good time to attach to the triad thing has formed. Okay? But it also is more stable this way than on that way. So that's how this forms. Finally, what seems to be going on is that cooperation and competition between these two mobilities and the two time scales involved. There is a time scale on how long a cluster can survive and the time scale in which particles can come and join. They compete and collaborate. And it is the result of that competition and collaboration I'm now just guessing wildly. I don't have proof because there are many more things have to be done to even understand the proof. So the summary is that dynamically driven grains with shapes that allow two modes of locomotion, such as both sliding and rolling, such as spheres or donuts, produce robust and useful self-organized structures that do not occur so efficiently with sliders or rollers alone in the same parameter space in the same comparable times. Rollers hardly do anything. They're very, very unstable. You have to make them static in your parameter space with higher friction when it's just on the side. Right? Now, the second one is not so important. So it is basically the whole problem, this entire class of problems. If you look back and go to the earlier papers where everything is written in far greater detail, you will see that everything depends on systems toggling. A particle toggles between a state of sliding and a state of rolling. In those cases, this case, this is not so important, but this is the general statement. And it might be interesting to explore this paradigm more extensively. That is, if you give a system of particles two different mobilities in general, then can they produce certain structures? And we had some discussion about what protocol means. So I am claiming it's protocol insensitive, but that it's within quotes, that I cannot guarantee that all protocols will give you this, but to the extent we understand, crystallite will form, gas will be there. No, you do not know exactly where the crystallite is. You will know it if you roughen the surface in a local place. Suppose you make a hole, which is cheating, of course, then you will get a cluster there, right? But unless you are in this weak pinning regime, then by and large, this is the net result. So, this is the summary, but what I'd like to do is to end with some outrageous statement, okay? And the outrageous statement is chemotaxis. So we know of another case in nature where a particle, in this case a bacteria, has two mobilities. One is run and one is tumble. So what these E. coli do is they have flagella. And these flagella are these little tentacles which stick out. And they sometimes rotate around each other and run towards towards food. And then they stop, undo the flagella to ensure that the food gradient, which is what the flagella are measuring in all directions, that hasn't changed yet. So once that has, once they know that the food direction has not changed, then they wrap up and go again. So they do two things, one to find food and the other to go towards it. Okay, so some this is Howard Berg's famous, very, very famous video. And you see these guys, there are these guys, oh, I don't know what is going on with the video here. You see, this is where they have opened up the flagella and they're tumbling. And the other ones, when the flagella are opened up, you can see them, they're moving along, right? So you get, do two types of things. Now there is another thing, is bacterial motility, yet another video where you see these things of things becoming static and then moving. In these, there is no evidence of clustering of any sort that I'm talking about. So what and this is the place where you can see it. Let me just say that with this very tentative state of our understanding of what really is going on, we decided that the way to think about this is to say that is this notion of two mobilities, and we it's just a playing of games with the words, rolling and stumbling. That is, you roll, which is your preferred movement, and then you stumble, and then you fall down, and that forms the core or a nucleus where the crystal actually forms. All right? But this is a very subtle, how should I say, competition between the nature of drive, the local mobility of the particle, and this mysterious, short-range interaction, attractive interaction, without which none of this will make sense. That they will, when they come close together, they stay together. And once the triad forms, however, then it's very clear that they're kinetically stuck until you can overcome the potential. Overcome the sliding potential. So this is, these are the two main results. And I'll just play this again for you to look at it for the nth time. And you will notice that it is now, they are not always forming, getting together. It's only when they're close enough to form a tree that the rest happens. Okay, so thank you. let me just stop it, right? See, you must be sick of it.
Is it really clear that attractive interaction is needed for anything except the very final stage of actually sticking? Because as Sanjib was saying, for example, inelastic effects should already, kind of cause these things to clump. One thing one can do is simply study it in a sort of computer recreation without any attractive interaction, and just see if that works.
It works. In computer, it works, but
I mean,
without an attractive interaction.
Yeah, so the point is that attractive interaction is just for kind of sealing the final stage. I think you don't otherwise.
Right. I mean, but what I'm saying that you don't need attractive interaction.
Yeah.
But repulsive interaction for sure won't do this.
Yeah, sure. You can compete with this with
repulsive interaction. Then if it is charged, because we are done with charge, and nothing like this ever happens. Everything is just completely, yeah.
But in other respects, a lot of the physics is similar to motility-induced phase separation, because you have persistently moving objects. Here, the persistent motion is because of the imposed orbital shaking. They're persistently moving objects that get in each other's way. It's mostly that, right? It's a novel way of, it's similar physics, except that the persistent motion is imposed by large-scale swirling.
Yeah, so, I wish I understood MIPS better to, answer these questions very clearly, because it has been suggested, among many suggestions. Active matter was also suggested. I don't know but
your
point is that, mobility here is not inherent to the particle. It is created by the situation in which the particle exists. So, if mobility was inherent to the particle, then when the gases were removed, they will not reach energy.
Right.
So that will argue against a simple MIPS. Because why would you now create the ones that were already part of the cluster? Why do they go out?
Right. No, I agree completely. There are many features that are different, but roughly speaking, you have persistently moving objects, which once they get in each other's way, can't get out of each other's way.
I think that, the point is that the formation of the triad is central to formation of a structure. And that a triad is geometrically unable to do anything other than slide. And that friction coefficient is so large that in the drive range, the triad is immobile. And that gives you a seed. However, you have to also remember that it is susceptible to be broken by a projectile particle coming and breaking it out. So before that happens, something else has to happen. And when sufficiently, as it grows larger and larger, your ability to dislodge it becomes harder and harder. In that big crystallite, all the action is at the edges and nothing is happening in the center. The center is completely static.
Yeah, I agree.
Deepak.
So do you ever find cases where you form two triads slightly different and they compete for their growth?
The answer is not as triads, but ripening does happen. That means if there are two crystallites, one is larger than the other, the little one will sacrifice to be part of the bigger one. But I don't think we have evidence, I don't recall evidence of actually tracking from two triads, but two clusters, one large, one small, then ripening happens.
Hello, hi sir. Sorry. No, so I was just wondering about this protocol independence. In one case, if you're just quenching very fast, then you got this lot of different crystallites, right? Whereas,
That's correct.
yeah,
That's right.
so I mean, how fast
So-
you quench, that seems to matter.
Yeah, sure. I mean, what I meant to say is that if you are in the phase diagram, if you look at the phase diagram, I've gotten out of it. Yeah, so correct. So the point is that this is sort of quasi-static,
Yeah.
if you like, ramping. And in that regime, if for example, if you wait for a very long time, do you know that the exact same thing will happen? You already know that there is hysteresis. So there are, quenching was just to demonstrate the fact that time scales are important in the problem. So if you go very quickly down, the system was trying to form clusters, but the clusters didn't form enough time, which is what Deepak asked, to coalesce together to form a larger crystal. So you get a distribution of sizes of particles, but you notice that single particles do exist. And 2, 3, 4, 5, many sort of distribution of things happen. So in that sense, you are right that protocol not for quench, but protocol insensitivity is a thermodynamic kind of thing. And here it's like, if I do it quasi-statically, will I?
And do you get glossy clusters when you have polydispersity? Or has anybody done this?
No, I don't think it has been done. There are innumerable variations that are needed to be done. So I'm doubting if we will ever have enough for a paper. But it's a peculiar result which wasn't expected. If you look at the other papers which were published, you will see enough answers to these questions, but they were done for a cylinder. A cylinder was rotated. And there is some lot more interesting stuff happens, but it is too complicated to explain in a short talk. You might want to take a look at that. There is a lot more information about numbers. But yes, I mean, whether the attractive interaction is essential, I think without attractive interaction, it doesn't. Simulations say attractive is essential.
So have you also looked at the properties of the gas outside? Like, for example, what is the velocity distribution?
No, we haven't. They more or less come to some kind of a uniform, fairly uniform velocity distribution. That is, it's not spread out.
More or less constant velocity, and that's more or less
constant velocity.
And that depends on the how fast.
As soon as they hit the boundary, have a collision with the boundary, then it gets a kick, but then it settles into a velocity. So the velocity distribution, I think, my guess is very sharply peaked. It's basically, mu v equals f. So it's that.
There's one last question there, please.
Hello, sir. In the movie, roll and tumble movie, some shape was getting formed, like elongated in one way, slightly hexagonal in shape. So can you say something about that?
Which one?
Yeah, means if you can say something about why this shape only.
No, that's just
not this one. The first one you showed.
Which one? I showed you two.
Yeah.
This one?
Yeah.
Sorry. I'll gladly show you later, but if there is a general point you wish to make.
Yeah, it appears to be slightly hexagonal in shape. So is there anything particular about this experiment or?
It's always hexagonal. It's a triangular lattice.
Okay.
I mean, we have never seen any other lattice other than triangle.
Okay, so let's finish this session and let's thank Shobha again. Now